Hello, this is Mrs. Johnson. This is MAT 221, Calculus 1. We're in section 2.5, talking about limits involving infinity. So in this section, we're going to investigate the global behavior of functions, and in particular, whether their graphs approach asymptotes, vertical or horizontal. Now in pre-calculus, we talked about the end behavior of functions, and we talked about that behavior of what it looks like at the tail ends. And we talked about using the concept of increasing without bound or decreasing without bound or so forth. Today we're going to talk about more of these ideas of limits that involve infinity. So let's first talk about infinite limits. That is, limits as x goes to positive or negative infinity. These are limits when we talk about finite limits as x approaches negative or positive infinity. It's called the tail end behavior. In other words, as the input goes to positive or negative infinity. It's called the right tail as we go toward positive infinity, and the left tail behavior as x approaches negative infinity. Now I'm going to look at the classic rectangular hyperbola 1 over x and just look a little bit about this function here, first looking at its tail ends. As x approaches positive infinity, we notice that this hyperbolic function is tending closer and closer to an output, a y value, of 0. We also feel that this is true as x approaches negative infinity. So as x approaches positive infinity, we notice that the curve tends toward an output or targets a value of y equals 0. Never reaches it, by the way, but targets that value. And as x approaches negative infinity, this also happens. So as the denominator gets larger and larger, the value of the fraction is getting smaller and smaller. 1 over 100, 1 over 1,000, 1 over a million, 1 over 10 million. So the idea of as x gets really, really large, the value of the function is nearing 0. This is actually what we call the definition of a horizontal asymptote. We say a horizontal asymptote exists if the limit as x approaches positive infinity equals some number b, or the limit as x approaches negative infinity is equal to some number b. Now, in this case, the target value is the same for both the left and right tails. As I approach infinity and as I approach negative infinity, this curve happens to have the same targeting value of 0. So in our case, y equals 0, or the x-axis, would be my horizontal asymptote. Notice horizontal asymptotes have the equation y equals a number. Now, how many horizontal asymptotes could we have on any given function? Now in this function we have one horizontal asymptote, but there are many functions that have no horizontal asymptotes. There's no limiting value as we head toward positive or negative infinity. But other functions might have two horizontal asymptotes, one as x approaches positive infinity and one as x approaches negative infinity. So it depends on the function we're looking at, but a horizontal asymptote of any given function, there can be at most 2, sometimes 1, and sometimes none. So let's look at another example. Let's see if we can analyze it a little bit first before we actually look at the function. As x approaches infinity of this function, this is an algebraic function. I have a linear over a root function, which is not a polynomial. So this is called an algebraic function. But I do notice as x gets really, really big, this 1 in the denominator gets really insignificant as x goes toward infinity, because the x and the x squared are kind of take over as x gets really, really large. That plus 1 doesn't really mean that much. So the function as x approaches infinity will look a lot like this function, the 1 not meaning much. Now notice I could not do this in short-term behavior, but in long-term behavior I can do this, because as x gets increasingly large, the value of that 1 really doesn't make that significant difference to the function. Now, if I'm putting in a positive value for x, the numerator will be positive, and if I put a positive number in for x in the denominator will also be positive because I'm squaring it, but a square and a square root also undo each other. So because I'm putting in a positive number here in both the numerator and denominator, I could reduce this to, well, that's really a lot like x over x. And anything over itself except for 0 is actually 1. So I did a little bit of algebra here and a little bit of thinking through the problem to say as x approaches infinity, it looks like this has a targeting value, this function has a targeting value of 1, meaning that y equals 1 is a horizontal asymptote for this function. Here's the actual function. As x is approaching infinity, so as x gets increasingly larger, notice my targeting value for my output is targeting 1. Now, why does the left tail look like this? I could do this same procedure again using the left tail, putting a negative infinity here. The 1 still doesn't mean much, but at this point, when I square my function, I have a negative in the numerator and a positive in the denominator, and squaring the square root undoes each other. But I would have a negative x value in the numerator because I'm going toward negative infinity, and a positive value in the denominator because I squared that denominator. So a negative divided by a positive x would equal negative 1. So notice as I come toward negative infinity, I get a horizontal asymptote of y equals negative 1. All right, let's look at another function. This one's a little bit tricky. Sometimes we'd have to throw this into Mathematica to actually look and see if we have a limiting value here. So I want to find the limit as x approaches infinity. What's happening to the sine function as x gets bigger and bigger? Well, the sine function simply oscillates between -1 and +1 as it moves from 0 to positive infinity. However, the denominator is getting really, really large, 100, 1,000, 1,000,000. The sine function simply going up and down between -1 and +1. If I graph this function on Mathematica or on a calculator, it would actually look like this. As x is approaching positive infinity, my curve is what's called oscillating back and forth, but it's called a tapered oscillating function in that the numerator is simply going back and forth between a negative and positive value, but the denominator is getting huge. So as I target infinity toward x equals infinity, this function actually appears to have a limit as x approaches infinity of 0. We can actually prove this using the Squeeze Theorem. Now, I skipped the Squeeze Theorem in an earlier section, but I'm going to just really briefly show you it here. We're squeezing the function between two common functions and taking the limit of each. And when I do, I get the limit is between 0 and 0, therefore that limit is equal to 0. Don't worry about understanding the Squeeze Theorem just yet because I did skip it in an earlier section, but we'll talk more about this in Calculus 2 as we talk about tending to infinity and convergence and divergence of functions. Okay, let's go back to Calc 1 here. I also want you to notice as x approaches 0, notice as x approaches 0 here, the sine of 0 is equal to 0, but x is also approaching 0. And notice I feel like I should have a vertical asymptote here, but I don't. There's a hole in the function because the function is not defined at x equals 0. Can't see the hole because the axis is clogging it up. But this actually is still having a limit as x approaches 1. We'll talk about that one in just a minute. Here's another limit to infinity. As x approaches infinity, let's use some of our rules for limits here. We know that the limit of a quotient is equal to the quotient of the limits. We know the limit of a sum is equal to the sum of the limits. And we know that when we have a constant multiplied by a function, we can pull that constant out to the front. So I'm doing a little bit of my limit laws here. I know that in this case, the x's will cancel, so I get the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine of x over x. Well, I just did this one. The limit of this one as x approaches infinity was equal to 0. And the limit to y equals 5, which is a constant function, we know that the limit of a constant is simply equal to that constant. So I get 5 plus 0, or 5. So here again, we could do a little bit of analytic work here. We could also put this on Mathematica to see what this graph looks like as x approaches infinity. We could also use limit tables to look at these limit tables and see what this function looks like as x approaches infinity. All right, let's try another one. Remember, this is one we did earlier. If we look at this one as x approaches infinity, now this is not to say we can't factor that denominator, and notice never will the denominator be 0 because no matter what I put in here for x, I'm going to square it. So even negative numbers, when I square it, will be positive. So the denominator will always be positive. This is saying, what do I do as x approaches infinity? Well, again, let's look at a limit table here. I did this in Mathematica. As x is getting larger and larger and larger, my output value is getting closer and closer to 1. We'll do this in class when we look at limit tables to infinity. Here's the actual graph of the function that I graphed. And you can see as x increases without bound, the y value, or the output value of this function, is getting closer and closer to 1. Now in pre-calculus, remember we did leading term divided by leading term, and the plus and minus 1, again, don't really mean that much as x approaches infinity. So if we had x squared divided by x squared, that would be canceling each other out to be y equals 1. So notice in both ends, I have a horizontal asymptote of y equals 1. So notice there's many different ways that the graph can approach a horizontal asymptote. I could have something like this where the function goes like this and approaches some horizontal asymptote. We could have an exponentially decaying function so that you notice, by the way, that the horizontal asymptote, I can pass through that horizontal asymptote. I just have it as I tend toward infinity, the curve seems to level off. Here's another one. This is tampering, getting closer and closer to 0. Or this one, I could say I have a left tail behavior toward y equals L, but a right tail behavior is going toward infinity. Here, the right tail behavior was going toward L, but the left tail behavior was going toward infinity. Or you could have something like this. The left tail behavior is going toward L, and the right tail behavior looks like it's going toward negative infinity. These are all different ways that we could approach a horizontal asymptote. Now, some functions we said before, notice that there's many ways for a graph of f to approach it, and some functions have more than one horizontal asymptote. Now, I referred to this earlier. As x approaches positive infinity, this has a horizontal asymptote of y equals negative 1. So its end behavior toward the right approaches an output of negative 1. But the left tail behavior, as we head toward negative infinity, looks like the curve is leveling off to an output of y equals 2. So y equals 2 is the second horizontal asymptote as x approaches negative infinity. Remember, we can have at most 2 horizontal asymptotes. We sometimes have 1 and sometimes none. So let's look at the what's called infinite limits. That is, limits as x approaches a given number that actually tend toward infinity. So if we look at this function, as the denominator approaches 0, the value of the fraction is actually getting really, really large. As x is equal to 1 over 1/10th, 1 over 1/100th, 1 over 1/1,000,000th, the actual value of the function is getting very, very large. And you can see that as x approaches from the positive side, the curve is tending to a really large number. As x approaches from the negative side, it's approaching a really large negative number, or toward negative infinity. So if the denominator is positive, then the fraction will head toward positive infinity. If the fraction is negative, then my limit is heading toward negative infinity. And we can definitely see this from the graph of this function, this hyperbolic function. Notice we say that the limit does not exist as x approaches 0, but we could say each tends toward infinity or negative infinity. But still, there are 2 different targets, so the limit as x approaches 0 does not exist.